Okay, so first of all, I would like to, there were two questions I left unattended to in the last class. So I would like to do that as briefly as I can. I asked whether you were familiar with the photoelectric effect, Compton scattering, and peer production. And that's what I'd like to start with first. So these effects or phenomena are of interest when we are referring to gamma ray interactions with the formation. It's not limited to gamma ray effects with formation. They are widely used in physics, but when it comes to gamma ray interactions with the formation, the photoelectric effect, Compton scattering, pair production come into view. Now note that the natural gamma ray, the density logging tool, the neutron logging tool, they are all based on the principle of radioactivity. However, the natural gamma ray and spectral gamma ray are basically made up of detectors. There is no, you don't bombard the formation with any form of radiation. However, for the other tools, whether you want to talk about the density log or the neutron log, it involves you bombarding the formation with a gamma ray source. And these three interactions actually depend on the gamma ray, the energy of the gamma ray, which is incident on the formation. So it says the probability of a specific gamma ray interaction occurring will depend on the atomic number of the material and on the energy of the gamma ray. So the atomic number of the material is a function of what is being bombarded, while the energy of the gamma ray is a function of your gamma ray source. And the things I have left off earlier here says that for a gamma ray source, and you can look this up later, of course, you need a gamma ray source. You need certain detectors that would detect back scattering, and then you need to shield your source from the detector so that what you are reading in the detectors is not incident energy, but either reflected or refracted energy. That said, I will like to go quickly. So in this slide, you would see on the left, you have the atomic number of the material on the y-axis, and then you have the gamma ray energy on the x-axis. So you see that as the incident gamma ray energy increases, you transist, in general terms, from the photoelectric effect to the Compton scattering effect to pair production. Of course, there are a few others. It's regions of dominance of the three principal gamma ray scattering or absorption mechanisms are a function of the energy of the gamma ray and the atomic number of the scattering material, that's of the formation in this case. So these effects are evidenced, or they are experienced depending on the energy, the energy of the incident gamma ray. So I will just speak briefly about, let me start with the photoelectric effect. So the photoelectric effect results from the interaction of a gamma ray or incident gamma ray on with the material. In this process, the incident gamma ray disappears and it transfers the energy to a bound electron. So the gamma ray is incident on a material. The incident gamma ray is lost, as it were, or is all absorbed by a bound electron. If the incident gamma ray energy is large enough, an electron is ejected from the atom and it begins to interact with adjacent material. Normally, the ejected electron is replaced by a less tightly bound electron, accompanied by an emission of some X-rays. For most Earth malformations, the photoelectric effect becomes a dominant process for gamma ray energies less than 100 kilo electron volts. And as I say that, keep this view graph in view. Note that this particular scale is in mega electron volts. That one is kilo. Yeah, so that tells for the scale. So for gamma ray, there's an incident gamma ray. All the energy of the gamma ray is absorbed into a bound electron. Depending on the energy of the incident ray, the electron may be ejected, and then that interacts with the formation. The Compton scattering, of course, the Compton scattering is experienced. The energy required for Compton scattering is higher than that for photoelectric effect. So moving up the gamma ray energy scale, the next dominant process is gamma ray scattering, which involves interaction of gamma rays and the individual electrons. In this process, in which only part of the gamma ray is impacted to the electron. So in the first process, basically because of it's a low energy effect, all the gamma ray energy is absorbed. But in this one, only part of the gamma ray energy is impacted to the electron, and the remaining gamma ray bounces off the material in form of reduced energy. Unlike photoelectric effect, the cross-section for Compton scattering changes relatively slowly with energy. When it says the attenuation of gamma rays due to Compton scattering will be a function of bulk density. If I go back, briefly, I'll make reference to this. So you might wonder, just before I stop this. So the attenuation of gamma rays due to Compton scattering will be a function of the bulk density and the ratio of the Z to A. Z to A is, please let me confirm what Z to A is all about. So the Z is atomic number, while A is atomic mass. Z is atomic number, A is atomic mass. And I think something that is important to note is that Compton scattering is a higher energy effect as compared to photoelectric effect. And therefore, the photoelectric effect, it says photoelectric effect is sensitive to the atomic number. The atomic number is directly related to the lithology of the material. So and that's why when you have the photoelectric log, you are usually, so that's why the photoelectric log, which is at times is put together on the same track, or where you have the porosity logs, it's used to give some further information on the lithology of the rock. As for Compton scattering is more related to the bulk density of the material. And as I said, Compton effect is a scatter reaction with the orbiting electrons of the target material. Therefore, the probability of interaction is controlled by the number of electrons, which is equal to Z. For most common materials, there is a constant atomic number to atomic mass constant. Hence, since the rock bulk density is dominated by atomic mass, The following relationships connect electron density to Compton effect. So this effect, so Compton scattering is the principle actually which the bulk density tool works on or works around. For time and importance, I wouldn't discuss the pair, but for the pair production, just for completeness, what happens is that the gamma ray energy is incident on the material, and then it's all absorbed, and then instead of just either an electron being ejected, an electron-positron pair is formed. For this one, I wouldn't really talk much about this particular process, but the photoelectric effect and Compton scattering have more bearing towards the traditional tools than this particular one. So the basic thing is these are effects having to do with the incident energy from the gamma ray source and the nature of the material that it is incident on. Okay, so let me use this opportunity to